Have you ever looked at a mathematical statement and just had a feeling? A feeling that something was a little off? Well, today, we're diving into the world of set theory to sharpen that intuition. We're going to learn how to tell the difference between something that's truly solid and something that just looks that way.
You know, in math, you really get to play two awesome but totally different roles. On one hand, you've got the breaker. This is the detective, the skeptic, the one who hunts for that single tiny flaw that can bring a whole argument crashing down. And on the other hand, you've got the builder, the architect who designs these beautiful, perfect, totally airtight proofs that can stand up to anything. Today, we're going to learn how to be both, starting with the art of the takedown.
All right, time to put on our detective hats. For this first part, think of us as investigators. We've been given a statement, and our mission is to see if it's really as true as it claims to be. We're hunting for one specific piece of evidence, something called a counterexample.
And here it is. This is our case file. The statement claims that if you take any three sets, A, B, and C, as long as A is a subset of B, then this whole intersection thingy on the right will always equal the empty set, no exceptions. Our job? To figure out if that's legit or if we can find just one scenario where it all falls apart.
So what's our main weapon in this investigation? It's the counterexample. And the beautiful thing about it is that we don't need some long, complicated argument. All we need is one single, specific example where the rule doesn't work. It's like finding the logical smoking gun. You find it, and boom, case closed.
Okay, so let's get strategic. To break this statement, our entire goal is to make that final intersection not empty, right? We need to cook up some sets A, B, and C, where at the end of the day, there's at least one element left inside that intersection.
Let's think this through like a true breaker. If we want something to be in that final intersection, we need an element. Let's just call it X that checks two boxes. The first box is easy. X has to be inside of set A. Simple enough.
Now for the second box. That very same X also needs to be in the complement of B intersect C. So what does that really mean? It just means that X can't be in both B and C at the same time. And of course, we have to do all this while still following the original rule that A has to be a subset of B.
So after a little bit of detective work, check these out. These are the sets that are going to blow this case wide open. We've got our universal set. We'll say A is 1, 2, B is 1, 2, 3, and C is 3, 4, 5. First thing, let's just check. Is A a subset of B? Yep, both 1 and 2 are in B. So we're good there. Now, let's see if this setup breaks the claim.
Let's run the numbers. First up, what's the intersection of B and C? Well, looking at them, the only thing they have in common is the number 3. So B intersects C is just 3. Now, what's the complement of that? It's everything in our universal set that isn't 3. So that gives us 1, 2, 4, 5. And now for the final move. We take our set A, which is 1, 2, and we intersect it with that complement we just figured out, 1, 2, 4, 5. So, what do they have in common? Well, look at that. They have 1, 2 in common. And that is definitely not the empty set.
And there it is, the smoking gun. We were told the result would always be empty, but we found a case where the result is 1, 2. We found our counterexample. That means the original statement is officially, without a doubt, false. The breaker's job here is done. Case closed. Okay, let's totally switch gears. We've seen how fun it can be to break something, but now it's time to become the builder. Our job is no longer to find a flaw, but to do the opposite. To construct something perfect, something indestructible, a formal proof that shows a statement is always true, no matter what. So here's our blueprint. We need to prove that for absolutely any sets A and B you can dream up, the intersection of A with the union of A and B is always just A. This is actually a pretty famous rule called an absorption law. And unlike last time, we can't just plug in one example. We have to prove it's true for everything.
So, how in the world do you build a proof like that? We use a really clever and powerful technique, sometimes called the two-way street proof. The idea is simple. To prove two sets are equal, you just have to prove it's a two-way street. First, you show everything in the left set is also in the right one. Then you flip it and show everything in the right set is also in the left one. If you can prove both of those things, they have to be the exact same set.
Okay, let's start with the first direction. We're going to show that the thing on the left is a subset of A. We start by just grabbing any old element from that left-hand set. Let's call it X. Now, by the very definition of an intersection, if X is in there, that means X has to be an A, and X has to be an A union B. Well, hold on a second. We just said X is in A. That's all we needed to show. Any element from the left is also on the right. Part 1 of our proof is done. That was kinda easy, right?
Now for the other direction of our two-way street. We need to prove that A is a subset of that more complicated thing on the left. So this time, let's start by grabbing an element X from set A. Now think about it. By the definition of a union, if X is in A, it's gotta be in A union B, right? So now we actually know two things about our X. It's in A, and it's in A union B. So what does the definition of an intersection tell us? It tells us X must be in the intersection of those two sets. We just proved any element from the right side is also on the left.
And there you have it. We did it. We walked down both sides of the street. We proved the left side is a subset of the right, and we proved the right side is a subset of the left. Because we've shown it works in both directions, the only possible conclusion is that those two sets are absolutely 100% equal. We have built an unbreakable proof. The statement is true.
So let's just zoom out. You now have two incredibly powerful new tools in your mathematical toolkit. First, you've got the breaker technique. If you want to take down a big general statement, all you need is one single counterexample. And second, you've got the builder technique. If you want to prove two sets are equal for all time, you build that solid two-way street proof showing they're subsets of each other.
And that kind of leaves us with a fun question to think about. Which one feels more satisfying to you? Is it that thrill of the hunt, playing detective and finding that one fatal flaw that makes a whole statement crumble? Or is it the quiet pride of the architect, carefully building a perfect, elegant proof that you know will stand forever? The breaker or the builder? It's something to think about. Thanks for tuning in.